Gases are a little bit different compared to solids and liquids. And so in this video, let's focus on these key differences from the thermal expansion point of view. One of the differences can be understood by taking an example. So imagine you have a plastic bottle which is completely filled with, say, a liquid like water. Or you could also have this bottle completely filled with, say, sand. So either you take some liquid or some solid and completely fill it. Then try to crush it. What do you think is going to happen? First of all, great experiment. If you're not tried, do it. But what you will see is that nothing happens. The bottle will not budge. It will not get squeezed. It will not get crushed. Nothing's going to happen. All right. Now you take out all the water or you take out all the sand, which means what remains now is air. And again, try to crush it. Again, try to crush it. What's going to happen? This time, the bottle will get crushed. In other words, the volume of a liquid or a solid does not change with pressure. That's the key thing to understand. We have applied pressure, we have increased the pressure by squeezing it, but the volume of the liquid has not changed. So the volume does not depend on pressure, and this is the way I'll write it. This is dependency, and it does not depend. But when it comes to a gas, the volume does depend on pressure. Does depend on pressure. Again, this is not equal to, I'm just saying it depends on pressure. Because notice when we increase the pressure over here, when we try to squeeze it, the bottle got crushed and the volume decreased. Now our goal over here is to calculate how much the volume of a gas changes with temperature, not pressure. We don't want the volume to change with pressure. So what should we do? Well, we should make sure the pressure does not change. And therefore, for a gas, to calculate change in volume, to calculate volume changes, and the way we calculate volume changes is by calculating this number called as the volume expansion coefficient. And volume expansion coefficient is just the change in volume per unit volume per unit change in temperature. That's how we calculate how the volume changes with temperature. And we've discussed about this in previous videos, so if you need more clarity, then it's better to go back and watch that video. But anyways, if you want to calculate this, we need to keep pressure, constant. Now, we didn't have to worry about this for liquids and solids, because pressure doesn't affect the volume at all. So whether you keep the pressure constant or you don't do it or you change the pressure, it wouldn't matter to us at all. So we didn't have to worry about pressure in the previous cases, but when it comes to gas, we have to make sure this remains a constant. That's one big difference between gases and solids and liquids. Another difference can be seen from a table. This table is telling us the values of alpha V and alpha L. Let's focus on alpha V. Of alpha V for different materials. All right. Now here's a question. Could we predict the alpha V value of say gold theoretically? Could we do that? Could we just figure this out that it was 42? The answer is no, not likely. These numbers were found experimentally. Theoretically, it would be extremely complicated. I have no idea how we would do that. And the reason for that is because we have no idea how the volume of these things change with temperature. We don't know about it. So there's no way we can derive it. However, with gas, the story is a little different. We do know how the volume of a gas changes with temperature. And since we already know that, and we'll talk about that, don't worry, but since we already know that, we can figure out what would be the alpha V value of a gas theoretically, at least approximately, we can figure it out. All right, so let's go ahead and do that. So let's get rid of this table. So what is the connection between volume of a gas and temperature of a gas? Can you think of any expression connecting volume and temperature of a gas? I think you've already learned one. It's called the ideal gas equation. Ideal gas equation. And the equation says if you take pressure and you multiply it by volume, PV equals N, the number of moles, R, which is a constant, we call that as the gas constant, times T, the absolute temperature in Kelvin. Now in reality, most real gases don't obey this equation, but they come pretty close to this. Almost all gases, under certain conditions, they come pretty close to obeying this equation. And so we can approximate almost all our gas as an ideal gas and then figure out what is the alpha V value for such an ideal gas. Now to calculate the change in the volume, we need to change the temperature by keeping the pressure constant. All right, so let's do that. Let's say initially the temperature is T1 and the volume is V1. So initially we would have an equation P V1 equals nRT1. And let's say finally the temperature changes to T2. The temperature changes to T2, which makes the volume change to V2. And so our final equation would be PV2 equals nRT2. Now to calculate the changes, let's subtract these two equations. Let's do 2 minus 1. So we'll do 2 minus 1. On the left-hand side, P would be a constant, and you would have in bracket V2 minus V1 because we're subtracting, right? And V2 minus V1 is delta V. That's the change in volume. That would be equal to, on the right-hand side, NR. They are constants, they don't change, but in the bracket we'd have T2 minus T1. That would be delta T. That would be delta T. Now, from this equation, we can calculate what delta V is, the change in volume, but we want to calculate how much the volume changes per unit volume, per unit temperature change. So let's go ahead and divide this equation by V delta T. So let's do that over here. V delta T on this side. We'll divide it by V delta T on this side. The delta T cancels out over here. And notice we now have nR divided by V. nR divided by V is just P by T. So this can be further written as P divided by T. Divided by T. And the P goes, and notice now the left-hand side is what we want. Change in volume, per unit change in temperature. And we call that as alpha V. And notice we have now calculated what alpha V is. We couldn't do this for solids or liquids, but we have done that for gas. For solids and liquids, this number was pretty much a constant. Pretty much. But for gases, not at all. Notice it depends on temperature. At higher temperatures, the volume expansion coefficient is lower. That means as the temperature increases, gases expand lesser and lesser. All right? The second thing to note is that for solids and liquids, different material expands differently. But for gases, since most gas behave almost ideal, for almost all gases, we have pretty much the same value of alpha V. We can even go ahead and calculate this at some temperature. Let's say we'll do that at room temperature. So if we do that at room temperature, the room temperature is about 300 Kelvin. So alpha V would be, let's see, 1 over 300 Kelvin. What would that be? Well, 1 divided by 3 is 0.3 times 10 to the power minus 2 Kelvin inverse. But let's convert this to 10 power minus 6. That's how it is in the table. We'll get back the table in a second. So to convert that 10 power minus 6, we will shift the decimal 4 places towards the right. That'll give us 3,000 times 10 power minus 6 Kelvin inverse. All right, now let's bring back the table. Here it is. We can now fill it up for gas. We get about 3,000 times 10 to the power minus 6. Here it is, 10 power minus 6. And this only works at room temperature, and we have to keep the pressure constant, and that's an approximate value. Yeah, all these things are there. But anyways, if we compare this value with that of liquids or solids, you see gases are the one that expand the most when you heat them up. All right. And just one last interesting thing we can think about is that when we build a thermometer, the idea is that we put a liquid like say mercury or alcohol in glass. And the idea is if the temperature changes, glass doesn't expand much, but the liquid expands a lot. But guess what? We can now build something called as the gas thermometer by putting a gas inside a glass container. That would be even better thermometer because gases expand much more. In fact, the most precise thermometers today are gas thermometers, and one of them are called as the constant pressure gas thermometers. So the idea is we keep the pressure over there constant, and as the temperature changes, its volume changes, and just by calculating how much the volume has changed, we can figure out very accurately how much the temperature has changed. Gas thermometers.